Welcome! In this video, I'll show you how to solve problem 6.13 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem asks us the following. It says, find the lowest order relativistic correction to the energy levels of the one-dimensional harmonic oscillator. And as a hint, they say use the technique of problem 2.37, but that's going to come into play later. So what do we do here? How do we go about this? Well, here we want to remember what we found while we were deriving the relativistic formula. So what we found is that the relativistic correction to first order is minus 1 over 2mc squared, e squared minus 2e, expectation value of V plus expectation value of the potential squared. And this is what we found, and afterward we said, okay, V is the potential for the hydrogen atom, and we kept going. But in this time we will use that the potential is the potential for the harmonic oscillator. And of course the energy will be the energy levels of the harmonic oscillator as well, right? So n plus 1/2 h bar omega. So we want to plug all of this in here. So we get minus 1 over 2mc squared, and then we have the energy squared, which gives us n plus 1/2, and then h bar omega, all of this squared, so squared, 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 minus 2e, which is n plus 1/2 h bar omega, and then the potential of the expectation value of the potential, which is the expectation value of 1/2 m omega squared x squared plus, and now the expectation value of the potential squared, which is 1/4 m squared omega to the 4th power x to the 4th power. Okay, so what does this give us? Now let's simplify this a little bit. So this doesn't change at all. So we still have n plus 1/2 squared, h bar squared, w squared. But now here we can take out the constants from the expectation value. So the 2 cancels out with this. So we get minus n plus 1/2 h bar m omega cubed and the expectation value of x. And then we have plus, and here we can take out our constants as well. So 1/4 m squared omega to the 4th power, expectation value of x to the 4th power. And this is what we now need to solve. So to find the corrections, we need to find the expectation value of x squared of the harmonic oscillator and the expectation value of x to the 4th of the harmonic oscillator. You can find them however you want. In problem 2.37, I think it was, we already calculated this, so for that reason I won't really bother doing it again. If you're unsure, unsure how to do it, I'm gonna post the link to that problem in the description, and there you can see how we find it more easily, right? And I'll also explain it in greater detail. So what we found in that problem is that the expectation value of x squared is n plus 1/2 h bar m omega. So let's plug it in. So we get n plus 1/2 h bar divided by m omega. So the m's cancel out. This m cancels out this. We get h bar squared omega squared. And also we get n plus 1/2 squared. So notice that now these two parts cancel out. So we are left with, right, the first order correction for the relativistic energy ends up being minus 1 over 2mc squared times 1/4 m squared omega to the 4th power, expectation value of x to the 4th power. And this will be minus m omega to the 4th power divided by 8c squared. And of course, times the expectation value of x to the 4th power. So now our challenge will be to find x to the 4th power. Now this is where we will apply the techniques that we used in 2.37. right, in that other problem. I will of course explain how to do it. What we did back then was basically use the raising and lowering operators to be able to find everything that we need. So as a reminder, but again, I went into it in greater detail back then, but as a reminder, we could write our position operator x as minus I divided by the square root of 2m omega, and then times a plus minus a minus. So from this, we can find x squared, which will be this thing squared. So minus 1 divided by 2m omega squared. And now this thing squared, so a plus squared minus a plus a minus minus a minus a plus. Of course, a plus and a minus don't commute, so you can't just write, oh, 2 times a plus a minus or 2 times a minus a plus. You can't do it, right? Again, in the video about problem 2.37, I show also in greater detail why that doesn't work. And then finally, plus a minus squared. Okay, so x to the 4th power is this thing squared. So the first part squared gives us 1 over 4m squared w to the 4th power. And then we get this thing squared. That is going to be a lot of terms. So in order for us to save us some time, let's look at it in the following way. So let me move this. And because I'll use it in a moment. So I will copy this and write it twice. So this and paste it, and then again. So we now want to use this product or do this product. But notice that our goal is to apply this to some state n and then take the expectation value with that same n. And why do I say this? Because as we saw the last time, or basically in the few couple of videos where we worked with raising and lowering operators, right? Just to make it very explicitly, I will write it here. So if we have a plus acting on psi n, we get square root of n plus 1 h bar omega times psi n plus 1. And if we have a minus acting on psi n, we get square root of n h bar omega psi n minus 1. Why is this so relevant? Because if, right, we basically let me do it like this. So this is equal to n, all of this n. If we let these things act on n, n will change. And unless we raise and lower the level the same amounts of time, we will get 0. Why? Let me show you the first example. So when we do this, we get n and then sandwiched with 1 over, I guess I can take this outside so it's a bit cleaner. So let me take the constants outside, 4m squared omega to the 4th. And then we have bra of n. And now look at this. We have a plus to the 4th power n. Now, what is this? This will give us some number, right? Something. This will give us something times n to the plus 4. So we can take the alpha outside and we end up with the inner product between n and n plus 4. But the states are orthogonal, so that is 0. Okay, so unless we raise and lower the same amount of times, we will get 0. And that is very helpful because that means that we don't need to write down every single term, only those where we have the same amount of raising and lowering operators. Okay, so when we do this product, we don't get the same amount, so we don't write it. This times this, same. Times this, same. Times this, there we go. Here we have 2 times raising and 2 times lowering. That is something that we can do. Now, this term times this is not the same number, but times this it is. So minus a plus a minus times minus, so we get a plus, a plus a minus. Now we multiply this with this part, so we get plus a minus a plus. Then we multiply with this part, but that again gives us 0. Then we have this, maybe let's change color. So this times this, again 0. times this part that is not 0. So we get plus a minus a plus a plus a minus. And now we multiply with this. So we get plus a minus a plus a minus a plus, and times this last part, again 0. Finally, a minus will only give us a non-zero component with a plus squared. So plus a minus squared, a plus squared, and all of that acting on n. Okay, so now we just need to apply the raising and lowering operators a lot of times. So we got our constants here, m squared omega to the fourth. Unfortunately, none of these terms are exactly the same. We have every single permutation. You could use basically the commutators of a plus and a minus to move them around and get similar something similar. That could be, but I'm just going to do it the brute force way. So let's begin. Let's apply the lowering operator twice. So we get a plus squared, and if we apply the lowering operator once, we get, as we saw before, the square root of n h bar omega. And then we apply it again to a state where we have n minus 1, right, h bar omega, because the state had been changed. Again, I'll go into this in more detail in the other video. I do recommend you watch it first. And then we have our new state, which is n minus 2. Okay, so this comes from only a minus squared. We can, of course, write it a bit cleaner later, right? Putting together the h bar and omega, but we'll do that later. Okay, now I'll do this one in detail, and then we will be able to figure out what everything else is as well. So first we apply a minus, right? So let's write this as a plus, a minus, a plus. So first we apply a minus, and we get square root of n h bar omega n minus 1. But then we apply a plus. And when we do that, a plus is square root of n plus 1. But our current n is n minus 1. So we have to multiply this thing, right? So I'm going to make some room so that I can show it. So we have n minus 1. And we now have to multiply it by the square root of n minus 1 plus 1, and then h bar omega. So what this means is that we get n h bar omega again, right? So basically we get n h bar omega, and this is now n again. So state n. And then we want to apply a plus, a minus, again. And that is what we just applied. So we just applied a plus, a minus, and we got n h bar omega. So we are going to get another time n h bar omega. So we get n squared h bar squared omega squared in state n. Okay, what about these other cases? Let's see. So here we have plus, maybe let's change colors. So plus, a minus, and now we apply h plus, which is square root of n plus 1 h bar omega. And then times the state n plus 1. And now let's apply the lowering operator, which gives us square root of the current state, which is n plus 1 h bar omega. And then we multiply by the new state n, right? So when we multiply these two together, we get this thing squared and simply state n. Now that we already applied this, we are going to apply the lowering operator onto this, which gives us an additional square root of n h bar omega of n minus 1. And then onto this, we apply the raising operator, which is square root of n minus 1 plus 1 h bar omega, which gives us simply n h bar omega again, which makes this squared, and we are left with state n again. So basically here we have n times n plus 1 h bar squared omega squared. Now notice that we are constantly having these same combinations of a plus and a minus. So we might as well slowly begin to find some tactics to find them sooner. So for example, a plus, a minus, we have already calculated. And we know what it is. So we have a minus, a plus, and then when we apply a minus, we get square root of nh bar omega. And then when we apply a plus, we get nh bar omega again. So I already know that we will get n times h bar omega, right? And it will be squared inside the square root, so we lose the square root. And we will be in state n. Now, what about a minus, a plus? We also calculated it very recently, right? We know that that will simply give us, from a plus, we get square root of n plus 1 h bar omega. Then we apply lowering operator, which gives us square root of n plus 1 h bar omega. And we are still in state n. So basically, we multiply by n plus 1 h bar omega, so this squared, right? So it's now going a lot faster. So then we have this part, which is a minus a plus, which we just saw is n plus 1, and we basically get it twice. So this new part will be n plus 1 squared h bar squared omega squared. And finally, we have to apply the raising operator twice and then the lowering operator twice. So what does that mean? That means that let's see, so we have a minus squared, and first we apply the raising operator twice, so we get n plus 1 h bar omega, and then we get n plus 2 h bar omega. And we are left with state n plus 2. And now we need to apply the lowering operator twice, which gives us an additional n plus 2 h bar omega. So this is from doing it once. And then we get n plus 1 h bar omega. So we get this thing squared, and we are back to simply state n. And using the exact same logic, of course, going back to our very first term here, we are going to get this thing squared, right? We apply the raising operator, we get n minus 1, then we apply it again, and we get n, just n, and with the h bars omegas, of course. So let's rewrite this. Squared, squared, n. So there we go. Now the n's and everything is simply a constant, so we can simply take them out of the inner product, and we get 1 over 4 m squared omega to the 4th power. And now let's hope we didn't make a mistake. Now everything has h bar squared omega squared, so we can actually factor them out. So we get h bar squared omega squared, and then we get n times n minus 1 plus n squared plus n squared plus n, I guess I just multiplied through immediately there, plus n squared plus n, right from here. Then we get n plus 1 squared, so that is plus n squared plus 2n plus 1. And then from here we get n plus 1, n plus 2, which gives us n squared plus 3n plus 2. Of course, this still multiplies this inner product, which is 1, right? Any nth state is going to be normalized. This is the nth state of the harmonic oscillator. That's why that happens. And let's now write this one explicitly, because I wrote all others explicitly. So n squared minus n. Let's see. So this minus n will cancel out any other minus n. So let's say these. Now, this is simply the expectation value of x to the 4th, just to remind us. And then we have h bar squared divided by 4 m squared omega squared, and right, canceling out these two things. and then product of, let's see, 1, 2, 3, 4, 5, 6. 6n squared. And then we have n's. So 1n, 2, 3, 6 plus 6n. And then we have 2 plus 1 plus 3. So there we go. We found the expectation value of x to the 4th power. So let's plug it in here. So this is minus m omega to the 4th power 8c squared times, and I already forgot what this was. So this is h bar squared divided by 4m squared omega squared times 6n squared plus 6n plus 3. Okay, so let's see. We can simplify the omegas a little bit. So there's a few things to simplify. So now this is minus m omega squared h bar squared divided by 8 times 4, which is 32. And then we have, well, m squared down here. So I guess that cancels out this m. So we get mc squared. So all right, we took this and this, this and this, this. Okay, and this multiplies 6n squared plus 6n plus 3. So finally, we can factor out a 3 from here, right? So 3, 3, 3. So we get 3 and 2, 2, 1. And this right here is the relativistic correction for the quantum harmonic oscillator. Now, the procedure, as you can see, it wasn't difficult in itself. It was simply annoying. So what we had to do was just start off with our formula. And basically, if you have any sort of potential that you want to find the relativistic correction for, this is it, right? This is what we want to use. This is, of course, in one dimension. But if you have a one-dimensional potential, you can use this. Of course, you may get some complicated expectation values that you need to calculate, but well, if you can calculate them, then it's fine. You could also have just found these expectation values by integrating or something like that. That's also perfectly valid. It's up to you in the end. So anyways, I hope that this was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe consider checking out my Patreon and supporting me there. I'll see you in the next video. Thank you very much for watching.